Good day everyone. In the last video, I've shown you how to add two floating point numbers together. But in that example, we have adapted numbers with the same exponent. In this video, I'm going to show you a different example where the numbers have different exponents. We are using the same antithesis to make our computation shorter. But this time, the second number, instead of having rather having an exponent of 6, we'll have it an exponent of 8. So let us review the process of doing this. Now, since the numbers have different exponents, we are going to choose the number with the smaller exponent, and we will float the binary to the left several times until it has the same value as that of the bigger exponent, during which we can already start adding the matrices. So in this example, the first exponent is 6 being 0, 0, 1, 1, 0. And the second exponent is 8 being 0, 1, 0, 0, 0. Which means that we will deal with this because this is the smaller exponent. We are going to float the binary point to the left twice so that this 6 will become 8 because floating it once to the left will make it 7. Floating it another one will make it 8. So now they will have the same exponent. So let me head over to our first computation of the same value of this is the same value that we had. Let me head over to our solution sheet. Let's copy it here. So take note, we have the same mantisa 1 1 1 0 0 0 1 1 1 0 1 1. We have the same mantisa here. Let me just adjust before doing that. Let me adjust the weights of the table the way we do it before. So this is our mantisa, and if we head over to this, we'll have the same value 1 0 0 1 1 0 0 and 0 0. So what we need to do is to float it to the left twice because our exponent is 6. We'll make it 8. So what we'll do is we'll copy this table and we'll start floating after which. To float it to the we have to float it to the left, which means that there are two zeros here. We will float the binary point to the left. So therefore, first we will move this here, and then this 0 will transfer it here. So we'll have that, okay, and this spillover is deleted, okay, and then since the exponent now is 7 because we have floated to the left. Now we'll float this once again to the left by moving the mantisa to the right. Okay. We have an error here. Let's find it right. Just correct the error anyway. Okay. Then we'll just delete this. We have another underflow, and we'll put it here. Okay. So therefore, this is now our new exponent. Okay, and then to compute the value, we will use this. Okay, we'll use this formula where we now have our exponent as 8, and we'll now have this as 2 to the 8, 2 raised to the 8, which is 256. And our decimal equivalent is the exponent times the mantisa. This is 140. So now we have the same exponent as of the second number. So the second number being an exponent of 1000, we'll just have to convert again. Okay, so we'll copy our traditional sheet. Anyway, we can just copy our previous solution. The second, I think we have it here. Okay, we have it here. This is the right one. Find out so that we don't have to fill it up again. We start. Yes, this is the right one. So we just have to copy this and put it out in our solution sheet. Okay. So this is the same number. Okay. Let's copy the Antisa. Find out if this is the same number. Okay. Put it here. This is the same as our previous example. No, this is not the same, so we'll just have to delete this and encode the number again. So we'll have 111 followed by four zeros followed by one and two zeros. Is that correct? 111 followed by four zeros followed by one and two zeros. Okay. Followed by one and two zeros. That's correct now. So this is our mantisa, 0.51268. But this time our exponent is also 8. So we just copy this and our mantis we will have this, okay, times this. We have 132. Okay. Oh, I'm sorry, I'm lost. No? I think we are making the mistake here because yeah. Let's delete this. Let's do that again. No, with a different. It's just this times this. Okay. This is our first number. Yes. And our no, we haven't moved this yet. Okay. That's the reason why I made the mistake. Anyway, let me just copy this again. Control X and two positions. Okay. Because we have shifted it to the left, we will discard the two positions. Let's the underflow here. We have discarded the position. So we have 54. 142 is our first decimal. Okay. We'll check that later because we have adjusted this already. Okay. We have adjusted it to have an exponent of 8. And then our second value is 111. Okay, with an this time we'll use an exponent of 8 also. Copy it here. And it will be 2 to the 8. So this will be equal to this times that 225. Okay, it's 225. Anyway, we will disregard that for the moment. What we are going to do now is to add the two mantisas together. Okay, we have this adjusted mantisa. Okay, it's our first adjusted no, it's our first adjusted mantisa. You copy it together so that they will be close together. It's useless to convert yet because they have a different. They are not the same yet. Press Control C. This is our first mantisa, and we will Control Shift E. Okay, and we'll put the borders here because the borders are gone. The second mantisa is this. This is the non-adjusted mantisa. We did not adjust this because this is the bigger exponent of 8. Control Shift G, make. Now we start our addition. Okay. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1 is 0. Carry 1. 1 plus 1 plus 0 is 0. Carry 1. Okay. 1 plus 0 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. And then we'll have 1 plus 1, which is 0. Carry 1. And then we'll have 1 0 plus 1. 1 plus 0 plus 1 is another 0. Carry 1. 1 plus 0 plus 1, this is another 0. Carry 1. Okay. So we have a 1 here. And then this is our binary point. Okay. So what we'll do is we'll copy this table and move over. We have an exponent of 8, remember? So we are going to copy this table and shift. I'm sorry. This is our value 0, uh, 0, 0, 0, 0, 1. This is our sum 0, 0, 1, 0. This is our sum. Now we have a carry or an overflow of 1. So what we'll do is we'll just move this to the right to be able to shift. Control X this and move this to the right. Okay. Anyway, this is 0. We'll delete that. Now we will place the 1 here. Okay. And that makes our new table. Now, what are the place values? Okay. What are the place values? Let us copy the place values. Here. And we will copy the sum, since this is the sum. Okay. So copy the formula because this is the sum here. We have 0.99. Okay. We are sure that this is 0.99. Is that correct? No, I'm sorry, no, not yet. But we are going to multiply this with the place values. We copy this. Okay. And this time we will copy again the formula corresponding to the place value, the quantities of the place values. Copy here. We have 0.50867. Now let's go back to our exponent. Our exponent is 1,000 or 8. But we have added we have shifted to the right. We have floated to the left. So our exponent now is, new exponent is 9. Okay, that's one. Because we have floated our binary point to the left once because of the carryover. So therefore this will be 9. Okay, and uh, 2 to the 9 is equal to 2 raised to this. Okay, and our new decimal is the product of our 2 to the exponent times the mantisa. So you have 260.5. Okay, the expected value is 260.5. Now our result is 268.75. We have a slight difference because we had an underflow when we shifted to the right. Take note, Control Shift E. That's what we have. So in our actual addition, we have 260.5. There's a difference because we only have 10-bit mantisa. And in that example, no, we did not exactly represent the values. We had an uh, we had an underflow when we shifted the mantisa to the right, especially two positions to the right. And we are only using 10-bit mantisas. So that explains the point on how to uh, two floating point numbers with different exponents. So we focus on the number with a smaller exponent, and we float it to the left. We float the binary point to the left by doing a right shift of all the digits. In this case, we have shifted it to the left, the binary point twice. So we are going to add the exponent by 2. So from 6, it became 8. Now, incidentally, when we added the two converted values together, we had a carryover of 1. So to represent this in binary, or rather in floating point, we have to shift the binary point to the left, and then float it to the left, and shift all digits to the right. Therefore, also losing a precision because we have split over a digit. Anyway, everything will be different in floating point numbers because in FPU floating point units because they are very long pieces. So I hope you see the point. We are going to have exercises and quizzes based on this. You review this video and I hope you appreciate it. Put a like, or if you don't like, you just click it there and ask your comments and your questions below in the comments below. And thanks for watching and bye for now.